All right, good morning. Today we're going to look at lines that intersect circles. So here's some vocab that we are going to learn today. Maybe you already know a couple or seen a couple before. We have chord, secant, tangent, and concentric. So we're going to go through those one by one really quickly so you guys can get to know them. So a chord is a segment whose endpoints lie in a circle. So let's try and draw that and see what it looks like. So we have a circle. So it's a segment. A segment, remember, doesn't have arrows on it. So it's a segment whose endpoints lie in a circle. Lie on a circle. So that would be a chord. This would be a chord. That would be a chord. It didn't quite make it to the end of the circle, but it did. So basically, it's just a segment. It's inside the circle, and it goes all the way to both ends. All right. So any of these would be chords, as long as their endpoints are on the circle. So there are an infinite amount of chords that we could draw with this, right? Sit here and all day do this. So that's what a chord is. Let's look at the next one. A secant is a line that intersects a circle at 2 points. So instead of a segment now, we have a line. So a secant, let's get our line here, is a line that intersects a circle at 2 points. So here's a line, and it intersects at 2 points. You may be saying, all lines intersect a circle at 2 points. That's actually not the case, which we'll learn in a second. So I can draw a million different lines that intersect this circle, right? At 2 points. All right, next is a tangent. So a tangent is a line in the same plane as a circle that intersects it at exactly 1 point. So a line that intersects a circle at exactly 1 point. So what this looks like is a line, and it just touches a tiny bit. There's exactly 1 point right there where the line and the circle intersect at, and that is actually called the point of tangency. So this is a tangent line. Tangent lines are very important, actually. About a whole semester of your 12th grade of calculus, we'll be working with these tangent lines. You'll find it a very important thing to know. So it's good you learn it right now. So a tangent line is a line in the same plane as a circle that intersects at exactly 1 point. So I think you understand it intersects at exactly 1 point. Also has to be in the same plane. We haven't looked at planes in a while. But remember, if I drew something like this, so it hits there, and then it's a dashed line. Remember that is kind of like 3 dimensions. So here it is behind the circle, and it comes up and touches it at 1 point, and then is in front of the circle. So that would be a tangent line that is not in the same plane. So this would not be a tangent line, not same plane, in case you're wondering about that part of the definition. So tangent lines, is there more than one tangent line? Yeah, we could draw tangent lines. There's probably an infinite amount of tangent lines as well. That would be a tangent line. It just intersects at exactly 1 point. I can draw another one over here. We want it just to barely touch that circle. So it's just intersecting at that 1 point. So it just goes and skips off of it and keeps going. That's a tangent line. It's very, very important, a tangent line. Make sure you remember that. All right. The last vocab here we have is concentric and tangent circles. So a concentric circle, what it is it's 2 circles with the same center. So if I have a circle here and a circle here, those would be concentric circles. They have the same center. Concentric, you can think of them as the same center. So they're the same center. The only thing different is going to be the radius, right? So this little guy has this radius, whereas the bigger circle has a different size radius, right? But they're coming from the exact same center. Tangent circles, I imagine you can guess what they are, is circles that touch at exactly one point. So I have a circle like that, and another circle. Try to draw it. Nope. Doesn't look like they're quite touching there, but we'll pretend that they are. So imagine these two circles are touching at exactly just one point. The smaller circle just grazes off the bigger circle. Those would be tangent circles. All right. And then I guess the only other kind of circles we could have if we have two circles would be something like this. So we have two circles that intersect, right? They don't have a special name or anything. Those would just be intersecting circles. These would not be concentric circles, and they would not be tangent circles. They're not concentric circles because they do not have the same center, and they're not tangent circles because they intersect at 2 points. So they're just two intersecting circles. All right, common tangent. So a common tangent is a line that is tangent to two circles. That is tangent to two circles. So let's think about that. We have a line that's tangent to two different circles. So I have to draw two circles. All right, we have two circles there. And then imagine, I'm going to try and draw this. I'm not sure how well it's going to work. We have a line. It's going to go something like, move it around a little bit. So we have a line. That's better. That is tangent to two circles. It's called a common tangent. So a common tangent has its tangent to two circles. We could also draw another common tangent to these two circles going through here. Yeah. So we have this line that we just drew. It's tangent right there and right there to the other one. So a common tangent is a line that is tangent to two circles. Something to think about. You can answer me in class. Could two concentric circles have a common tangent? Could two concentric circles have a common tangent? You can think about that one. Maybe draw it. All right. The last part of this section, we have a couple of theorems that go with these circles and tangents now that we know the vocabulary. So the first one, these theorems also don't have any special names, like the Pythagorean theorem has a special name. Some other theorems do. These don't have any special names, but it says if a line is tangent to a circle, then it is perpendicular to the radius. So if a line is tangent to a circle, let's try and draw that, then it is perpendicular to the radius. So we have a line that is tangent to a circle. And we have a point of tangency right there. So it says this line is perpendicular to the radius. So if we draw a radius from the center to the point of tangency, it's saying that this makes a right angle on both sides, right? 90-90. And that works with any tangent line. Any tangent line will be perpendicular to the radius. So if I draw another one over here, and we draw from the center of this circle, it will make a right angle. I know my lines aren't perfect, but it'll make a right angle there always, the radius and the tangent line. All right, then the second one we have here is two segments are tangent to a circle from the same external point, then the segments are congruent. So let's draw a circle. And we have some external point, it says. So I'm going to make this my external point. It says if we draw two tangent lines from this external point to the circle, then they're going to be congruent. So let's see. So if I draw something from this one to the circle, and this point, tangent that way, it's like it's tangent right here, and it's tangent right here. So what it's saying is this distance from the point to the point of tangency, and this distance from the point to the point of tangency are congruent. So we use this line to show that it's congruent, right? So those two are going to be congruent, always, always, always. If the lines are coming from the same external point and are tangent to the same circle, they're always going to be congruent. All right, so this is kind of a super problem that I developed going over these two theorems. So we have some variables, some circles, some tangent lines, a little mix of everything. So first, let's take a look and see what we have. So it looks like we have a circle here, and this circle has a radius of 3. All right. And we have a line connecting my radius to some point, right? We have this external point out here. It looks like this 2x is a tangent line. It's tangent right there at the point of tangency. And the same thing here, this is tangent there. So you should be thinking this theorem here, if two segments are tangent to a circle from the same external point, then the segments are congruent. So that means that this is congruent to this because they're both tangent to the same circle from the same external point. So if they're congruent, we can say this 2x is equal to this 6x minus 10, right? And we can solve for this x to figure out what these are by subtracting 6x from both sides, minus 6x, minus 6x. And we get negative 4x equals negative 10. All right, so now if I divide by negative 4, I get x is equal to positive 10 over 4, right? Which we could simplify to 5 halves, which we could simplify to 2.5. All right, so we know x is equal to 2.5, yeah? That means that this whole distance here would be 2 times 2.5. 2 times 2.5 is 5. So that whole distance is 5. That means this whole distance should be 5 also. 6 times 2.5 minus 10. See, 6 times 2.5 is going to be 15. 15 minus 10 is 5. So both of those are equal to 5. All right, so we got x figured out there. And we know that our tangent lines are both equal to 5. We have this missing y here, though, which we still need to solve for. I'm going to make some room in the meantime and erase. We're going to have to use the other theorem that we learned to solve for this y. So the other theorem says if we have a tangent line, the radius is perpendicular to the tangent line. And we know our radius is equal to 3. So if our radius is equal to 3, we have this side is equal to 5. This is going to be my hypotenuse here. So I can figure out what this whole side is going to be with the Pythagorean theorem. A squared plus b squared equals c squared, because it's a right triangle. So we know that this 3 and the 5 can be the a and the b, so 3 squared plus 5 squared is equal to c squared. 3 squared is 9, 5 squared is 25. So So 9 plus 25 is equal to c squared. 9 plus 25 is 34. So 34 equals c squared. And if I want to find c, I need to get rid of that squared. Opposite of squaring is a square root. So the square root of 34 is equal to c. I'm use my calculator and figure out what the square root of 34 is. My calculator tells me that it is 5.83. 5.83. So that means that this whole side here is equal to 5.83. So this whole amount in green here is equal to 5.83. Well, if the whole thing is equal to 5.83, and we know that this distance is 3, then y has to be what's left over. That's from our segment addition postulate from a while ago. So we know if this whole thing is equal to 5.83, it's equal to my two parts, this 3 and the y. So if I want to figure out what my y is, I subtract 3, 5.83 minus 3 is 2.83, which is equal to my y. That's a segment addition postulate, which we learned a while back, but we've been using kind of all year long. So this is what you'll be doing in the lesson in class, looking at these two different theorems, where the radius is perpendicular to a tangent line. You'll probably be using the Pythagorean theorem in that case. And then if we have two tangent lines, like these ones, that are tangent to the same circle, coming from the same point, we know that they're congruent, or they're equal. All right, I will see you guys in class.